Let me welcome everybody at the last spring TUKE Space Forum. Today's webinar is devoted to SWARM mission, ESA mission, and for the monitoring geomagnetic field. And the name of the presentation is SWARM mission and recent changes in the Earth's magnetic field. Finlay will present the SWARM mission. Chris is professor of geomagnetism at the TUKE Space at Technical University of Denmark. Finlay is professor of geomagnetism at TUKE Space, Technical University of Denmark. His work focuses on changes in Earth's magnetic field on timescales from millennia from minutes to millennia, exploring both observational and theoretical aspects. He has a master's degree in physics from the University of Oxford in the UK, and PhD in geophysics from the University of Leeds. He worked for 5 years as postdoctoral researcher and then as the Oberassistent at ETH Zurich before joining the Danish Technical University in 2011. In 2010, he was the lead author of International Geomagnetic Reference Field, and he was chair of the YAGA working group for V-mode from the 2011 to 2015. And in 2012, he was awarded the SEDI Dornbos Memorial Prize for outstanding work on the Earth's deep interior by young scientists. He worked extensively with the geomagnetic observation from the satellites and ground observatories, using this to probe the structure and dynamics of the Earth. This was my honor to present our today's speaker, Chris Finlay. Chris, could you hear me? Could you hear us?
Yes, Pavel, thanks for the nice introduction. Thank you.
Yeah. Please, you could share your screen, and we are very interested in your presentation.
Okay, I'll try to share now.
Okay.
Can you see my slides?
Yes, yes, perfect.
Okay, so let's go from here then.
Yes, please.
So good afternoon, everyone, and thanks for the invitation to talk to you today about the Earth's magnetic field and the SWARM mission that we're currently using to measure and observe the Earth's magnetic field to greater accuracy than has ever been done before from space. So this afternoon, I've spent about half an hour introducing you to some background on the Earth's magnetic field and discussing the SWARM mission and some of the, what I think are quite interesting results that we've been getting recently. So this is work together with various colleagues at TUKE Space, in particular Professor Niels Olsen, who's the scientific lead of the SWARM mission, and also Phil Livermore, who is at the University of Leeds in the UK. So I'd like to begin with a little background about the topic of interest. So what's the reason to have a mission at all to measure the Earth's magnetic field? So you all know that even though we don't see it all around us continuously, the Earth's magnetic field is a fundamental part of our natural environment. This magnetic field, so of course a magnetic field exerts a force on moving charged particles. And the Earth's magnetic field is generated in the core of the planet, and it provides a force around the Earth which deflects charged particles coming from the sun. So in a sense, the Earth's magnetic field is providing us with a protection against the solar wind. And 98% of the magnetic field that we measure originates within the Earth's core. One fundamental observation about the Earth's magnetic field is that this protective shield is not at all steady. It's continuously changing. And the way we can understand in terms of physics this change is written in this equation here. So this is what's called the magnetic induction equation. And this tells us that time changes of the magnetic field, that's something that we call secular variation. This is produced by the action of a moving conductor. In our case, this is within the core of the Earth, acting on the magnetic field. So this advects and stretches the magnetic field around, generating it and maintaining it. and we have ohmic diffusion because the liquid core is not a perfect conductor. So all changes in magnetic field are produced either by the motion of a conductor on the magnetic field or by the magnetic diffusion. So what we'd really like to do is to understand the process that's happening within the Earth's core to generate the Earth's magnetic field. And to do this, we can observe the time changes in the Earth's magnetic field, the secular variation, and then use this to get information about what the fundamental underlying dynamics are within the Earth's core. So there are lots of fundamental scientific questions here. So, for example, what is the structure of the motions of the liquid metal inside the core responsible for generating the magnetic field, for driving its changes? And also, we see time changes of the Earth's magnetic field on decades and less. What could be the origin of these so-called rapid changes? They're rapid on a geological timescale. So these are some fundamental questions that we would like to try and answer. And as you've seen here, these questions really are mostly concerned with what's happening in the core of our planet. So although this isn't very far away in astronomical or space physics terms, it's only 3,000 kilometers from us here in the Earth's surface, we know very little about the Earth's core. We know that the temperature there is very high, for 4,000 to 6,000 Kelvin, and the pressure is very strong, between 100 and 400 gigapascals. We know from seismology that it's mostly iron, perhaps nickel and some light elements, silicon and oxygen, and a high density, 10,000 kilograms per cubic meter. But it's also a rather counterintuitive place, because despite the fact that it's a place where there's motions of liquid metal, these motions of liquid metal are rather different from that we expect. And that's because of the very high temperatures and pressures. In fact, the motions in the Earth's core are very turbulent. The viscosity there is similar to water at room temperature. So we get vigorous turbulent motions, and these motions are fundamentally driven by the cooling of the planet, which produces large convection currents. But as I say, really there's a lot of uncertainty about what is really taking place in the Earth's core. And one of the few ways we can probe what's happening in this inaccessible place is through magnetic field measurements. So how do we go about measuring the Earth's magnetic field? Well, the traditional way to do this has been through a network of ground observatory stations. And so these are places, usually isolated places away from anthropogenic disturbance, where the magnetic field can be measured in a clean environment by tri-axis fluxgate magnetometers, such as this device shown here. And such observatories were set up originally by Gauss in the 1840s and have since spread all over the planet. But there's certainly a concentration of them in well-developed places like Europe and North America and Asia. And of course, we can't have such observatories in 70% of the Earth's surface where there are oceans. So this gives us difficulties in globally measuring the Earth's magnetic field. And because it's a global process, this made it difficult to study the underlying physics. So the real change in this topic in the space age has been the ability to measure the Earth's magnetic field from space. And there's been a series of satellites starting in 1999 with the Danish satellite Ørsted, and then the CHAMP satellite, which is shown here, launched by the Germans in 2000. And these have measured the Earth's magnetic field from space. The CHAMP mission finished in 2010, and in 2013, ESA launched the SWARM mission. So this is where SWARM comes into the picture. So we were really lacking a high quality magnetic field monitoring mission from space. And the SWARM mission was proposed by researchers in Denmark, Germany, and France to carry out the best ever survey of the Earth's magnetic field from space. So what does the SWARM mission consist of? Well, the SWARM mission consists of 3 satellites. So you may think SWARM, that implies many satellites. And in fact, the original plan was to have many, but as the way of these things tends to be, gradually with budgetary restrictions, the number of satellites was optimized. And eventually we got 3 satellites, 3 identical satellites for measuring the Earth's magnetic field. And these consist of a pair of 2 satellites flying very close together, separated by about 150 kilometers in the east-west direction, flying as a pair. And these are designed to measure gradients, east-west gradients in the magnetic field. And then we have a 3rd satellite, which is at a slightly higher altitude. So the lower pair are at about 450 kilometers altitude, so it's low Earth orbit. And the higher satellite is at about 500 kilometers, so about 50 kilometers higher up. And it has a slightly different altitude, a slightly different inclination. So it's drifting in local time compared to the lower pair. And this 3rd satellite that's in a different orbital plane, this allows us for the first time to distinguish between space and time variations of the magnetic field from space. If you only have 1 satellite and you measure the magnetic field in one position, and then you wait and you measure at a later time, and you make a different measurement, then you're never sure whether that difference is because your position has changed or because the magnetic field has changed in time. So when we have 3 satellites, we're able to better distinguish these spatial and temporal variations. So this is the basic configuration of the SWARM mission. What are the crucial instruments for measuring the vector magnetic field? So shown here on the left-hand side is a schematic picture of the 3 SWARM satellites, the 2 lower pair and the 3rd satellite higher up. And the crucial instruments for measuring the magnetic field are placed here on a boom that is away from the body of the satellite, where there are electronics and solar panels. And these have, of course, small currents associated with them, and that means disturbance in terms of the magnetic field. So we need to put the crucial instruments away from the body of the satellite on a boom. And there are 2 crucial instruments for measuring the magnetic field. Right at the end of the boom, there is an instrument. This is a French instrument that measures the strength or intensity of the magnetic field. And this is an absolute instrument, so it measures the magnetic field by a quantum mechanical effect, by a resonance of some helium atoms. And from measuring the frequency of this resonance, then you get directly the magnetic field strength. In addition, there's a second instrument which is shown here, and this is the vector magnetometer. So behind these covers and things, this is this vector magnetometer as it was in the laboratory before launch. And in this thing that looks a bit like a baseball is what's called a spherical coil magnetometer. So here you have a 3-axis coil with coils in 3 perpendicular directions with a very high accuracy, very low noise core in the center of the coils. And this is measuring the variations in the magnetic field by a flux gate principle. This is not an absolute instrument, so it must be calibrated using the measurements made by the absolute magnetometer. So that gives us measurements of the vector components of the magnetic field. Then this is only useful if you know the orientation of the satellite. So to get the orientation of the satellite, we have 3 star trackers. So these are cameras, very accurate cameras that are looking at the stars, and then matching to star catalogs to find the attitude, the direction of the satellite to very high accuracy. So then when we combine this attitude information along with the vector field information from the magnetometer, we have the vector magnetic field. And these vector magnetometers and star trackers, these were built and provided by TUKE Space. So these are the crucial instruments, and it's identical instruments on board all 3 satellites. So what's the current status of the SWARM mission? So after 6 years in space, so the 3 satellites were launched together in November 2013 in one launch, and then into an orbit just a little bit above 500 kilometers, altitude a bit above 500 kilometers. And then Swarm B was pushed upwards to a higher altitude, and Swarm Alpha and Charlie were pushed downwards to a lower altitude, and all 3 satellites have since been slowly descending. And this bottom panel is showing the local time of the ascending node of the different satellites as a function of time. So originally they were all in the same orbital plane on launch, and then gradually they have separated in time. So this local time separation was maximum here around 2018, and now they're actually drifting back into the same plane. So this drift of the local time drifts of the 2 planes is something that we allow to happen naturally, and we don't too much change this local time drift. So the 3 satellites are in good shape. We had a failure of the absolute magnetometer on one of the satellites, Swarm Charlie, but this was one of the lower pair, so it was in fact possible to use the absolute magnetometer on the other satellite to perform a calibration on the Swarm Charlie. So we've managed to find a workaround for losing the absolute magnetometer on Swarm Charlie. But apart from that, the performance of the instruments has been excellent, and there's no indications of any problems with degradation, and we really hope for a very long SWARM mission. So we're interested in slow time changes of the Earth's magnetic field happening on times of years and decades. So we would really like the SWARM mission to go on as long as possible. And it looks right now that we can expect from an instrument and operations point of view a long mission, barring some unexpected problems. So that's really great news. So let me now go on. That's a bit about the observations and the mission. So now let me go on and tell you how we actually use the data. So what we do is we build global models of the Earth's magnetic field from these vector field measurements that are collected by the satellites. And to do that, we use a spherical harmonic approach based on potential fields. So the first step is to say we can represent the magnetic field B as minus the gradient of a potential, a scalar potential V, which we can separate into an internal, a part due to internal sources and a part due to external sources. And then the internal sources, this scalar potential is the solutions to Laplace's equation in spherical polar coordinates is in terms of a spherical harmonic expansion. So P and M here is associated Legendre functions. So phi is longitude, theta is colatitude, r is radius. A is a reference radius, which we take to be the Earth's surface. So then we have coefficients, spherical harmonic coefficient, GMN, HMN, that we fit to our data in order to provide a good explanation. And these spherical harmonic coefficients are time dependent because the Earth's magnetic field is changing in time, and we expand these in terms of a basis of B-splines. We also have an expansion for the external part of the field due to sources not within the Earth, but out in the magnetosphere, which we also expand in terms of spherical harmonics, but to a lower spherical harmonic degree. And here we use a coordinate system that's based around magnetic dipole latitude. This is a more appropriate coordinate system for external fields. So the details of this are given in 2 papers by Niels Olsen and co-workers in 2006 and 2014. So then we have an inverse problem. So we'd like to find these model coefficients from the data. And to do that, we minimize a cost function, which consists of a weighted difference between the data and the model predictions, where the weights are given by a priori error estimates that we have for the different satellites. And then in addition, we minimize 2 norms measuring this temporal complexity of the magnetic field. So we try to find, in some sense, the simplest models in time that can fit the data. And I'm going to show you some results from a model which I built with about 11.5 million data that came from what we call geomagnetically quiet times. So this is times when solar disturbances were not very large. And in this model, I used data not only from SWARM, but also from previous satellite missions, CHAMP, Ørsted, and SAC-C, and also from ground observatories. So this is taking basically all the good quality satellite data we have for the last 20 years into account. And in the models, we're able to fit the SWARM data to within about 2 nanoteslas, considering the scalar data. And if we consider along track differences of the magnetic field data, we can fit along track differences to about 1/4 of a nanotesla. And considering differences between 2 different satellites, between the lower satellite pairs, we can fit to within 1/2 a nanotesla. And you should compare that to a typical strength of the Earth's magnetic field, which is perhaps 50,000 nanotesla. So we're really able to fit the data to a very high level of accuracy. And the models that I'm shown are freely available from this web page. So let me go on now to present some results. So this is a map showing the Earth's magnetic field intensity at the Earth's surface. So this is in red, the magnetic field is strong. In blue, the field is weak. And this was the field that we get from our model in 1999 when the Ørsted satellite was launched. And I'm going to then move forward in steps of 5 years. And by looking at the contours here, you'll see how the intensity of the Earth's magnetic field has changed. So I should mention this is clearly not a simple dipole field intensity. A simple dipole, you would have strongest field in the polar region and weakest field on the equator. You'd see that there is this strange region of weaker field that we know is present in the South Atlantic. So an interesting question is what's been happening to this region as we go forward in time. So here's the field 5 years later in 2004, then 2009, this was mainly with data from the CHAMP satellites. Then 2014.5, now we have the first data from SWARM available. And this was more recently in the middle of last year. So in the last 2 frames here, you'll see the changes that we've observed with the SWARM satellites. So what you can see is that this low field intensity region has expanded in size, and that there's a secondary region of weak field, which is appearing here to the southwest of Africa. And if I can, I'd like to show you this movie in another way. So let me try and share a screen again here. So this is a movie that's showing the development now just during the SWARM time. So this is starting in 2014, slightly different color scale here to emphasize this weak field anomaly. So let's play it going forward in time, and you can see the growth of this weak field anomaly and its development here, not just at the center of the weak field over South America, but also here closer to Africa. And there are interesting consequences for this weak field region. Let me show you a second movie now, which is this is an animation which shows on top of this South Atlantic anomaly, now plotted at satellite altitude, locations where we see memory upsets of the electronics on swarm. So the swarm is just any kind of satellite in low Earth orbit for this purposes. Oh, it seems this movie is not going to work. That's a shame. Okay. Perhaps I can come back to that one later. But if it had played, you would have seen that we get a lot of memory failures or memory upsets, I should say, in the South Atlantic anomaly region. This is because in this region we have a higher flux of radiation because the magnetic field is weaker there. The charged particles in the radiation belt come closer to Earth's surface in this region, or closer to low Earth orbit, and they are there's a larger radiation dose experienced by the satellites and more upsets. So this South Atlantic anomaly is clearly an important region to understand, and we don't well understand at the moment why it's changing and why it's evolving. This is a topic of active research. Another topic I wanted to mention is the motion that we see in the North Magnetic Pole. So what's shown here in this picture is, so the North Magnetic Pole is the position where the Earth's magnetic field is purely vertical. So this is the region in the Northern Hemisphere where the magnetic field lines are pointing, in fact, vertically downwards. And here the blue contours are showing this is the local direction of the horizontal magnetic field. So these lines also converge on the North Magnetic Pole. So I'll show you with a similar time sequence here: 1999, 2004, 2009, 2014, and more recently here in mid-2019. So what you see here is that there's a kind of surprisingly linear motion of the North Magnetic Pole, starting over near Canada and moving in the direction of Siberia. So this is, of course, something we've been interested in understanding, and we believe this is due to a difference in the balance between two concentrations of magnetic field that are seen over Canada and Siberia. So what's shown in these plots is, so this is the radial component of the magnetic field at the Earth's surface in the bottom row in 1999 and in the top row in 2019. The light blue contours are contours of the horizontal magnetic field, which is 0 at the North Magnetic Pole. And the path of the North Magnetic Pole is shown by the red stars here. So what's happened between 1999 and 2019 is that the field intensity, the radial field intensity over Canada has decreased, while that over Siberia has stayed constant. And we can see that even if we truncate the Earth's magnetic field at spherical harmonic degree 6, we still see that there is a strong, two patches of strong magnetic field, one over Canada and one over Siberia in 1999. And by 2019, the patch over Canada has basically disappeared. And the origin of this has to be in the Earth's core. And downward continuing to the Earth's core, we see this picture. So again, now here it's even clearer that this strong field patch over Canada has decreased. So what could be the possible reason for this? Well, we've taken the measurements we have of the changes in the Earth's magnetic field and used this magnetic induction equation that I showed you at the start to connect time changes of the magnetic field to motions of the liquid metal within the Earth's core. And that allows us to derive patterns of the fluid flow at the top of the Earth's core. And that's what's shown here in the blue, oh sorry, the green lines here are showing streamlines of the flow within the core. This is in 2018. So in general, there's a flow of liquid metal in the core that goes from high latitudes to low latitudes, over here at eastward longitudes, and then westward, and then back again at high latitudes. And this is rather symmetric between the two hemispheres. And what we've noticed is that between 1999 and 2019, there's been a change in this fluid flow, in particular over North America. And what has happened is that this previous flux concentration over North America has kind of been stretched out, elongated by the fluid flow. So there's been a strong intensification of the fluid flow here in this region. There's a kind of jet that's been established at very high latitudes. And we believe it's the change in this flow pattern beneath North America during this time that's caused the diminishing of the North American flux concentration. And this then has allowed the North Magnetic Pole to move from Canada over towards Siberia. Okay, I can see that the time is already going quite fast. So I'll maybe just show us a few last quick results about the structure of the secular variation. So that's the time variation of the magnetic field when we map it at the surface of the Earth's core. So when we take the time derivative of the Earth's magnetic field, and with our spherical harmonic models, we can downward continue that to the outer source region at the top of the Earth's core. We find there that much of the intense magnetic field change is happening at low latitudes, and also in this region in high northern latitudes. There's much less happening in the southern hemisphere or at mid latitudes. And we can also see detailed changes between 2014 when SWARM was launched and 2019. And it's these changes that we can then use to investigate the underlying core processes. If we zoom in then to this equatorial region where we can see interesting things happening, and we plot the second time derivative of the field as a function of longitude and time, we can see that at a fixed longitude, we get these oscillations in time with accelerations in a positive eastward direction, then westward, then eastward, then westward. So we're seeing some oscillations in the magnetic field at some certain longitudes. And there's also evidence for propagation of these disturbances westwards. So we have some hypotheses about how to explain this in terms of the motions within the core. But we need to be aware that what we're looking at is not the full picture. It's only what we can see with the observations we had. So it's a spatially band limited and temporally filtered version of the true magnetic field signal. And in order to do better, we really need to push to get higher resolution in both space and time. And this involves improving our processing and modeling schemes. And what's shown here is an example of a new attempt to go to higher temporal resolution. So I will, I think, skip over the details of this in the interests of time, and because I think I'm over time now, so I'll finish with a summary. So I've shown you how we now have more than 20 years of global magnetic field observations from space, and we have more than 6 years of data from the SWARM satellites. And this is allowing us to see changes in the Earth's magnetic field to a level of detail that we've never been able to do before. So it's allowing us to track in particular the expansion of the South Atlantic anomaly, the North Magnetic Pole motion, and the weakening of this North American magnetic flux patch. And we see subdecadal localized fluctuations, especially at low latitudes. And these are providing us with improved observational constraints on what's happening regarding the flow in the core. So in particular, we see there's decadal variability in the flow in the core, especially at high latitudes, close to what we call the tangent cylinder, which sits around the inner core. And we also see indications of waves arriving at the core surface at low latitudes. And we've been developing new ways of inverting the magnetic field data to study these processes. And looking forward, perhaps the most important thing for this subject is to have longer time series, so that the typical timescales here for changes in the Earth's magnetic field are years to decades. And so the thing we really need is long time series. So we're really looking forward to a long swarm mission. And the other thing that we really need is the noise source for all of this is really these ionospheric and magnetospheric current systems. And we need a better knowledge of these external current systems if we're to improve our inversions for the core processes. And there's some exciting work going on here trying to use platform magnetometers, calibrating them using the data from SWARM, and then using these to characterize more rapid changes in the magnetospheric and ionospheric currents using large constellation missions like the magnetometers on board Iridium, like Spire nanosats, which also have magnetometers, and even ESA missions like Cryosat. We found we can calibrate the platform magnetometer data on these missions and use them to help better characterize the Earth's magnetic field and the fast variations. Okay, so I think I'll finish up there and I'll hand back to you.
Thank you. Yeah, thank you very much for a very nice presentation indeed. And I could just wish you to very, very long swarm mission and disconnect me to the question. So please, could you stop sharing screen? I will share the questions.
Yes.
Okay, so okay, let's do it. It's generally desktop. Okay, here we are. Okay, so, okay, let's start with question. First one, most popular one. We have in total 17 questions. So, okay, let's start quickly. What is the most probable explanation of the origin of the South Atlantic anomaly?
Yeah, so the honest answer here is we don't know the origin of the South Atlantic anomaly. So one theory that, or one hypothesis that people have suggested is that there are these regions we can see at the core surface where the magnetic field is in the opposite direction to what we expect. So normally if you had a simple dipole, you would have the field lines coming out in one hemisphere and going back in the other hemisphere, okay? But we can see from the observations that there are regions where the magnetic field is reversed, okay? And so we call these reversed flux patches. So then what happens when you go up to the Earth's surface, you average over all of this magnetic field at the core mantle boundary. And when you average over things that are both what we call normal flux and reversed flux, then you get an overall weak intensity. Okay, so I think the answer is it's due to these reversed flux features. So that's the simple explanation. But then, of course, the question is, well, where do these reversed flux features come from? And that involves the convection processes within the Earth's core that we don't fully understand. Yeah.
And how long it will take? I mean, such an anomaly could stay there for I don't know, decades. I mean, thousands of years. How long it could stay there?
Yeah, so the time scale for convection in the outer core, the time scale for one overturn is about 80 years, okay? But when we look back, we have data on the Earth's magnetic field. We're fortunate to have data for many centuries because people were recording the magnetic field for navigational purposes. And what we can see is we can track these reversed flux patches certainly back to the time of Gauss. So these things have been around for at least a century, 150 years in fact, but they've been developing. They're not completely stationary. So certainly we can expect this thing to be around over the next decades, but the question really is how should we expect it to change? And what we see is that if these reversed, so there's more than one of these reversed flux features, and if these features gather in one location, if they kind of coalesce, then when we go up to the Earth's surface, we see that the weak field region is growing and weakening. So if these reversed flux features are gathering, then we should expect the South Atlantic anomaly to continue to grow and weaken. But we are not able to forecast how exactly these reverse flux features will move in the future. This is beyond our capabilities at the moment.
But it's possible that we have a couple of or a lot of such South Atlantic anomalies in the human history. I mean, in the thousands.
Yeah,
These are just appear and disappear. Yes.
Yes. Yes.
Oh,
I think if you, so this becomes the topic of paleomagnetism and archaeomagnetism, where the magnetic field is recorded in rocks. And if you go further back in Earth's history, then the problem is getting enough global coverage, right?
Yeah.
Because then you only have it in certain locations and at certain times when, for example, a volcano is erupting, or you get it in some sediment with a very, very poor time resolution. So these are the difficulties when we go further back in time. But there's strong evidence that we have had things like the South Atlantic anomaly many times in Earth's history. So I don't think there's anything kind of very unusual about this feature. We shouldn't be surprised that that is present at the moment.
Yeah. Yeah, there is a question a little bit connected to this one, but let's go to the from most popular to the to the less popular. So another question. Next question is, thank you very much for the answer of first one. Okay, yeah. What is the precision of the IGRF model in comparison with measurements?
Yeah.
Where is most precise and where we can find the biggest differences?
Yeah. So the IGRF matches. Measurements on board satellites and at ground observatories typically to within 10 nanotesla at the time the IGRF was built. So the IGRF is updated every 5 years. So what happens is the IGRF is most accurate. It's actually most accurate now because it's just been updated in 2020. And then gradually the error increases in time because what happens is a forecast is made for the magnetic field changes, but it's not very good because we can't do that very well. So that is why then in 5 years, we have to make an update.
Yeah, yeah.
So, so typically the error is 10 to 20 nanoteslas at the time it's built, and then it can grow up to maybe 100 nanoteslas at the time when the update happens. But I should mention that the IGRF is a very useful model, but it's perhaps not the highest accuracy model. It's well established and it's used by many people. But there are models, for example, the chaos model that we're producing at DTU, that one we're updating about every 3 to 4 months. So then we don't have this error due to the update problem. Yeah. And in that case, we're able to fit the swarm data to within 2 to 5 nanotesla. So that is much more accurate. And in that type of model, we also model the external magnetic fields, the magnetospheric fields. So the IGRF only represents its internal sources. So part of its inaccuracy is because it ignores some sources.
Yeah. So external field and also crustal field.
Sure. Also crustal field.
So sorry for this detail, but I will ask that if I will have magnetometer somewhere here, or I don't know, in Europe, and I will compare this one with the IGRF, and I will see in the quiet period, let's say 1% difference. What does it mean? I mean, there is some crustal magnetic field, or probably magnetometer is measuring with error, or what you will say?
Okay, it depends how good if you've got a good magnetometer, not one in your mobile phone, let's say.
Yeah, okay. Okay, I mean, someone which is on intermagnet, let's say.
Yes. So in this case, the largest discrepancy is due to the crustal effect.
Okay, so crustal.
And so this is typically, can be 110 to 100 nanoteslas. If you're sitting above a really big geological crustal anomaly, that could be even up to 1,000 nanotesla. But that's a static offset.
Yeah.
And the thing is, that's happening on a very local scale. And the IGRF is only characterizing things on large wavelength. So the IGRF only has a resolution, let's say, of some thousands of kilometers. So it can't possibly tell you what the local crustal anomaly where you are is. So, so that's the reason for this constant offset. But you could measure that for some months, and then you could take that off rather easily. Yeah.
Okay.
And then what's left, if you look at the quiet levels, then what you'd see would be daily variations. They have an amplitude of about 30 nanotesla. And then maybe if there was a storm, this would have amplitude, let's say, some hundreds of nanoteslas. And during quiet times, the magnetospheric currents, these feel this is some maybe 10 to 20 nanoteslas level. Yeah.
So this is very, please.
No, please.
Okay, so yeah, this is very interesting for me, especially that just I must continue with questions because audience is not whole in this field. So this is evergreen of our TUKE Space Forum. I mean, we have this question was answered by every one of the speakers yet, and so I will read it also. If you could have a budget like James Webb Space Telescope, approximately $10 billion, what space mission or experiment you will like to see to become reality?
Yeah, so from my perspective, yeah, I'm a big fan of long-term observations. I think this is very important in geophysics to have consistent long-term measurements. And I think it's not, everyone always wants the latest fancy mission. I would rather spend the money on ensuring we have several centuries of high quality, consistent measurement. Okay, so that's what I would put it in some long-term funding plan for long-term observation. Beyond that, I think what's really missing at the moment to go, for example, to higher resolution for the magnetic field, we need more satellites. So what I could imagine is maybe a large number of smaller satellites. So some kind of constellation where there's maybe one or two larger satellites like swarm type that can be used as a kind of reference benchmark, and then many smaller satellites that are varying through local time much faster. So then we could try to get some kind of more continuous model of the Earth's magnetic field. So of course, plenty of people are launching a lot of satellites these days. You only have to look at what's happening with SpaceX and so on. And not just them, also with the Spire constellation. And many of these missions have magnetometers on board for navigational purposes. So maybe even some of these can be used. But if I was given the budget, I would put up maybe 70 or 80 small satellites with good quality magnetometers to measure the kind of global structure of the magnetospheric and ionospheric fields, and then have some long-term sentinels that would last for many, many decades. Because the smaller satellites probably only last 3 to 4 years. Right? But you need big ones to stay up for longer, right? Yeah.
This is something new. I mean, we don't have a long-term mission, a dream here yet. And this is really interesting, very, very much. I think we still name the students Voyager as example of something which is really old and producing first scientific results. So,
yeah.
Nice.
I think in geomagnetism, we're very aware of this because we have beautiful long time series from many centuries. And we appreciate very much the work by scientists in earlier generations. And I think we should also think about the future scientists and provide data that is useful also in the long term. Yeah.
Yes. Thank you. Okay, next question. How far we are from the next Earth's pole reversals? When it will happen and how long it will take?
Yeah, so we don't know when it will happen. All I can tell you is that there's been hundreds of these events in the Earth's history, but you should be aware that they occur over geological times. So From the observations we have of previous reversals, they take on the order of 10,000 years. That's rather slow for a human, right? So that means that you don't need to worry about it happening tomorrow or even next decade, right? This is something that is really a process happening on a millennial timescale. So we can see that on average, there's about 2 to 3 reversals per million years, but this process is certainly not periodic. Definitely not. So you will often see in the media this argument that, oh, you have 2 or 3 polarity reversals per million years. Therefore, because the last one we had was 800,000 years ago, we're overdue. But this is incorrect because it assumes that the thing is periodic. There has been times where it's gone for 20 million years without there being a reversal, a so-called superchron. So you ask me how long it takes. Well, I don't understand the mechanism of reversals. So I can't tell you if the things we're seeing today are a precursor to a reversal, because we don't understand that process. So all I can tell you is that I'm certain there will be reversals coming in the future. That means in the geological future. But I think there's been fluctuations in the field intensity like those we see today many times. So I don't think there's any strong evidence that we're close to a reversal. And even if we were in the early stages of one, this would take several well, thousand years or tens of thousands of years. Yeah.
Maybe it's just I heard it a long time ago that sometimes in the history the evolution was faster, so sometimes was more gradual and sometimes it was more slower. Yeah. And does this gradual periods by chance somehow correlate with the reversals, so with more radiation over the Earth? I don't know, maybe you could comment on this. It's just...
Yeah, so you mean, for example, a reversal happening? Was there some...
Yeah, reversal happening every, I don't know, you say 20 million years. And when this happening for the, I don't know, 10,000 years, there is more radiation over the whole Earth. Yeah? So more radiation will mean basically more mutation and maybe faster evolution. So maybe this is what paleontology somehow record, and there is some correlation. I don't know. This is just curious.
Yeah, so this topic is much discussed. I think in terms of the simple question is there a correlation between extinction rates and reversals occurring, the occurrence of a reversal? And I think there's no strong evidence. So there has been papers that claim this, but then this has also been disputed. So, and I think that there's no evidence that every time a reversal happens, there's a mass extinction. No. I mean, your question is a bit more subtle, because you're saying during periods when there was many reversals, is there on average a difference in the amount of new species? For example, during something like the Cambrian explosion or something like this. And I think that is something that people certainly investigate. I mean, I think that this is still an active topic of disagreements and discussions, but it's certainly plausible. I mean, you could understand this from a mechanistic point of view, but I think the observations are very sparse, and it's difficult to prove this kind of connection.
Yeah. Yeah. Thank you. Okay. Next question. How do you extract the crustal magnetic field from the geomagnetic field from external and internal sources?
Yeah, so okay, for the crustal field, it's primarily static, whereas the other two are changing. Okay. So the one thing you can do is to look for the steady part, but then there is still a part of the core field that has a non-zero time average. So there, the usual thing that we do is we plot a power spectrum of the magnetic field intensity against the wavelength. And there we can see that there's a kind of knee at spherical harmonic degree 13. And at low spherical harmonic degree, it means long wavelength. The amount of power is decreasing very rapidly. And this is what you expect for a distant source. Whereas it's it's flat at a higher spherical harmonic degree. So we normally say that the part of the spectrum where which is flat is due to crustal sources, and this due to the steep decay is due to the core sources. So there's a separation based on the crustal field being static and also based on the wavelength. Yeah, but it's imperfect, this separation. There's an overlap region where we can't completely dissociate them. Regarding the external field from the internal field, this is the contribution of Gauss. So he did this beautiful piece of mathematics where he showed that you can separate mathematically internal and external sources. So you have part of your model that is parameterized in internal sources, part in external sources, and they have different radial dependencies. And if you have measurements of the full vector, so that means both the vertical and the horizontal part, you can separate these two. So that we can do mathematically.
Okay. Thank you.
Provided we have good global coverage, I should say. Yeah.
Okay, thank you. Next question is what was the most challenging part of the swarm satellite technology? What was most hard to develop, to build?
Yeah, so I think so. I'm a physicist. I haven't worked on the instruments directly myself, but from what I observed, that the big challenge is making sure that these satellites are magnetically clean. That means there's no possible currents due to other things. And in fact, even after Swarm was launched and there was a huge effort made to make sure they were as clean as possible, then there was an effect we hadn't expected, a thermoelectric current due to temperature gradients across the satellites, which give some very small signals, even though the magnetometers are away from the booms of the satellites. So therefore, that became a big detective job to try to characterize that from an engineering point of view and then to take it out. And that was possible, but that was a lot of work. So I think both in terms of, from an engineering point of view, yes, you need to make sure your instrument, you have a beautiful instrument, but then it's also the system level problem of how you ensure all these instruments are integrated correctly on the satellite, and you make sure that there's no unexpected sources of electrical currents that would disturb these very accurate magnetic measurements. Yeah.
Yes. Yes, sure. Interesting. So, thank you. Another question from Patrick. So, what is the resolution of vector field magnetometers?
Yeah. So, you mean accuracy or?
Well, we could ask Patrick. I think probably yes. What is small? I will rephrase it. Maybe I'm not correct, but I will say that he asking what smallest change of magnetic field you could measure.
Yes. So the calibration is to less than 0.3 nanotesla. Okay. So we can measure geophysical fluctuations that are bigger than 0.3 nanoteslas.
Yeah.
Yeah. So the vector magnetometers are calibrated to that level. Now, most of the disturbance, from my point of view, wanting to study the core, is not in fact instrument noise. It's other unmodeled signals that we don't know about. So there's plenty of magnetospheric and ionospheric and magnetospheric ionospheric coupling currents that change very rapidly in space and time. These are real geophysical signals, but they're not something we can model. So this is why we can only fit the data to, let's say, 2 or 3 nanotesla, while the magnetometers can measure to 0.3 nanotesla. So that's why sometimes we look at gradients or differences, because when we do that, we can take out a large part of the correlated error. Yeah.
Well, it's probably unlikely, but just come to my mind to be able to measure some artificial magnetic field from the ground. I don't know, from some big installation or something. I don't know, it's possible to do it from orbit by swarm.
Yeah, so I missed the question there. So
Yeah, sorry, I was just asking if you could measure some artificial magnetic field made by man on the Earth. I don't know, big,
yeah.
something. I don't know if you could measure it from orbit.
You mean in order for calibration purposes? Or
No,
something?
no, just we are so sensitive. You are measuring very sensitively or magnetic field on orbit. So maybe you measure not just the flashes and a lot of physics and a lot of nature, but maybe you are measuring something artificial, something which was made by the, I don't know, our civilization somehow.
Yeah, yeah, that's a good question. We haven't seen any obvious correlations of that of things, for example, correlated to locations of cities or something like that.
The city, for example, yeah.
But I mean, you would need very large currents, and if it's at all a localized source, yeah, of course the field is decreasing. Like
Yeah, sure.
So you need a very big current. Yeah.
Just back change. How much, how sensitive are you, man? Okay, so thank you. Okay, this is someone asking a funny question. Do you want to visit the magnetic pole?
Sure, why not? I think it's quite expensive to do, especially if it's in the middle of the ocean at high latitudes. People do it occasionally, but it's
Yeah, but, well, yeah, it will be interesting, of course. So, okay, another question. Next one. How? Sorry?
It's kind of romantic to go to the pole somehow. That's okay.
Yeah, it's something like 19th to 20th century, the adventure. Well, okay, this is an interesting question. How many people working currently at Swarm mission? How it is organized? Do you have regular meetings? Is there something different than in other missions? So generally, how is Swarm working on the management level?
So the Swarm mission, it's really from the scientist point of view, it's organized in two ways. There's something called Swarm Disk, which is the Swarm Data Innovation and Science Cluster. And this is the kind of collection of the key institutions that are working on Swarm data products. And then beyond that, there is, every year we have Swarm data quality workshops. And this is typically about 100 scientists are gathering, and there we discuss really Swarm data and the quality and the instruments and all the challenges. So this is a very active community, and this is driving also discussions about how we should optimize the future evolution of the orbits and so on, and planning for future missions and this kind of thing. So I would say there's maybe 100 to 200 really active scientists who are regularly attending these data quality workshops. And then beyond that, of course, sessions at larger conferences and this kind of thing. But so there's probably a kind of core group of this Swarm disk, which is maybe 30 to 40 scientists. And then this larger group of, let's say, users, active users, not just users, in fact, people deeply involved in the data, 100 to 200 people. And then beyond that, people who are using it more broadly for science studies. So it's a kind of hierarchy, but we're actually very happy with the way that ESA is organizing this, where the scientists get a lot of input into how the mission is developing. Yeah.
How many articles are produced every year from the Swarm data?
Oh, yeah, I don't know the answer to this on the top of my head. Okay. I would, yeah. You can find this out on the Swarm webpage. I'm not counting articles so regularly, but I would guess it's on the order of hundreds.
Yeah, that's enough. Yeah, hundreds. Okay, this magnitude. Okay, because there is question connected to this one. Okay, so how? But I will read next one. How look your typical working day? What consumes most of your time?
Yeah. So I would say my time is split between so research. That means using the Swarm data, kind of looking at the latest data checking its quality, building these global models of the magnetic field, and that probably takes up yeah, maybe 30 to 40% of my time. Then I've got teaching, so I'm teaching courses in the university on geomagnetism and inverse problems, and managing PhD students and research projects. This takes probably about half of my time. Yeah, and then the rest of the time is spent maybe doing some kind of outreach stuff, or university administration, this kind of fun activities. So, but research maybe if I'm lucky, 30% of the time. Yeah.
Yes. Okay. Thank you. Another question: what is the downlink of the mission?
Yeah.
How much of data you will transfer back to the Earth daily?
Yeah, I don't know the exact telemetry details, but I know it's happening. Yeah, well, so the orbits take about 90 minutes, but it's not being downlinked. I don't think on every orbit.
Mm-hmm.
So yeah, I have to admit I don't know. I'm an end user of the data in that sense. I'm not really involved in that. Yeah.
Yes. Yes. Okay. So here it's another. Next question is more notation than question. So, but you could comment on this. So, field anomaly in Central African Republic is sign of the meteorite impact half billion years ago. It is place where the rare black diamonds are excavated. So swarm can see the black diamonds from the orbit. So it's notation that wow.
Well, it can see the anomaly. It can see the anomaly. Yes.
Yeah, anomaly. But yes, you could. I mean, say like the literary sense that he sees diamonds. Okay, you know.
Yeah, I mean, I think nice. I think it's. Nice. But by the way, I think it's a topic of discussion. The origin of that anomaly. This is the Bangui anomaly in Central Africa. It's not. I mean, meteor impact is one plausible hypothesis, but other people have other ideas. But for sure, we see it. That's a big anomaly. Yeah.
It's nice hypothesis. I should say. Okay. Okay. What was the next question is, what was the original proposed number of satellites in Swarm project?
Yeah, I think it was 5 or 6, something like that. And then we had to do a lot of simulations to show what, I mean, with these kind of things, you always have to justify why you need so many satellites. And if you can't, if there's a way where money can be saved, and these are very expensive satellites. These are very large, heavy, one-off satellites.
What was the overall?
So that was the reason why they gradually went down to 3, because it was felt that we could still do this best ever survey with 3, even though as scientists we originally wanted more. Yeah.
Yeah. What was the overall budget of the Swarm? Well, till launch or till now?
Yeah, I don't know the exact number actually. It's
a lot of money.
Some maybe 2. Yeah, I don't want to say the wrong number.
Sure.
Maybe on the order of 100 million euro, 1 to 2 to 300 million euro, I think. But yeah, I think this is this is always evolving. Yeah.
Yeah, sure. Yes. And how much is the cost per year? I mean, just in connection that you want to work for decades. So it's maybe.
It's much smaller. I mean, the major cost was the development of the instrumentation, and the launch was very expensive and so on. The operation is relatively small once the satellites are there and operating. This is why it would be very foolish to stop the operation of the mission when you have excellent instruments up there, given the initial cost for development and launching. And of course, all the cost, you have to always remember this is money that's going back to the member states for the development of instruments and technology. So it's not a simple equation. Yeah.
And I saw on the figures the orbit decay, basically satellite is going a little bit down.
Yeah.
And do you have some engines on the satellites to increase orbit or?
Yes, so we have fuel, so we can actively control up and down. So yes, and so far we haven't done a lot of maneuvers. So we actually have a lot of fuel left. So the plan is to push them up again.
So you could stay there up for long, yeah?
Yeah, so the question of how long they stay up and when to push them up depends a lot on how strong the solar cycle is. So this tells you about how much drag you have.
Yeah, atmospheric drag, yes.
And so, of course, people do simulations for this, but you're never sure exactly it depends on how strong the solar cycle. If the solar cycle is stronger, you get more drag and then you come down faster. But our strategy is to use the fuel if possible to keep them up as long as we can. And then along the way to make some maneuvers to bring the satellites sometimes into alignment, which can be very nice for studying, especially ionospheric and field-aligned currents at high latitudes. There it's interesting to have the satellites close together, maybe not all the time, but in some certain times. So some fuel is spent kind of bringing the satellites to configurations for these specific experiments. But then otherwise we really aim so we will try to push them up before the next solar cycle is starting.
Yes.
Right. So maybe 2021, something like that. Then the plan is to push them up again, and then keep them up for as long as possible. Perhaps it could be interesting for them to come down in the next solar minimum. Yeah, because for mapping the crustal field and so on, you want the satellites as low as possible when the external activity level is as low as possible.
So, but generally, you like deep solar minima periods.
Well, for studying internal field, yes.
Yeah. And to keep satellites up there, I mean, to have low atmospheric drag.
To keep them up for a long time. So in fact, the current weak solar cycles is, that's fine for us who are interested in studying the core field at least.
So someone is beneficiary. Yeah. Okay, so well, this is interesting question. What geomagnetic models for field description during last 2 millennia? So I mean, IGRF period is excluded. I mean, from this question, and the last tens of thousands of years are most precise. So
yeah, so
this recommend some of such model for the last 2,000 years to be used.
Yeah, so I think the kind of one of the best established groups in this area is Monica Corta from GFZ and Kathy Constable from Scripps in San Diego. And they've made a series of models. They call it CalSK. I think it stands for Continuous Archaeomagnetic and Lake Sediment. I can't remember the full acronym, but this is a model that spans, so they have different models, some which only go back maybe 2,000 or 3,000 years and some which go maybe 10,000 years back. So I think this is kind of a model that people often compare to. And this contains as much as possible of these indirect measurements made from archaeomagnetic sources. These are archaeological artifacts that have been dated and studied in the lab to determine the magnetic field direction when they were formed. Also lake sediments, you can find the ancient magnetic field directions, at least from these. So I would say looking in that kind of model is a good start, but you should always bear in mind that there are uncertainties in these models because you're dealing with indirect measurements.
Yeah. Yes. Okay. Thank you. Okay. This is the question which we mentioned already in connection to what was already said. That in the best scenario, how long SWARM will work? You say as long as possible. Yes. Could it be for decades? Well,
so the thing that limits this is, well, on the one hand, it's instruments. So there must at some point be some degradation. If the instruments are operating in this radiation environment, especially each time they're flying through the South Atlantic anomaly. But right now, they look really good, and we see no trouble. So certainly within the SWARM community, we actively discuss the possibility of measurements out to 2030. And the other thing is these two lower satellites, Alpha and Charlie, they will probably come down first. And this higher up satellite swarm Bravo, it might stay up for a very long time. But whether or not how long precisely, as I said, depends on the level of solar activity. So we can't be certain about what, I can't give you a direct answer to that because I don't know how much atmospheric drag there'll be, because we don't know what the upcoming solar cycles will be. But it seems that we could at least be optimistic and say that we might get another full decade of data, provided it's supported by the space agency and provided there's no problem with the instruments and there's not a very strong solar cycle. Yeah.
Yes, yes. Well, let's hope for long operations.
Yeah.
Well, okay. This is question which is probably at wrong webinar. This is a question to another expert, but you could comment. Of course, number of satellites get increased. Do you have a way how to avoid a possible crash with other satellites in future?
Yeah. So I mean, it is an issue. This vision. Collision avoidance. So, I mean, ESA is very carefully keeping an eye on everything that's up there, but for sure, there's more and more satellites in low Earth orbit. That's for sure true. And there has been examples where Swarm has had to take, we had to move the Swarm satellites because there was a chance of collision.
How much times this happened in these 6 years of operations?
Oh, not very often, maybe a handful of times. But so of course, this is also a question of good communication and everyone knowing everything. And this is the job of the space agencies. And I think they're really, my impression is that this is a big priority for them. Of course, these are very expensive instruments, and they're really trying their best to avoid anything. And if there's a probability of a close match, then the mission manager has to make the decision whether or not to move the satellite and use some fuel. Okay, but so that's definitely a real active concern, and it will, I would say, be more and more the case, I guess. Yeah.
Okay, thank you. Okay, this is a question that you say there are hundreds of the articles from Swarm data. So which of them do you like most? Do you have some favorites?
Yeah, that's a good question, actually. Yeah. I mean, I like, there's been some work done by Carl Magnus Lundahl in Norway, where he's used the Swarm data to construct models of the polar ionospheric and magnetosphere ionospheric current systems. And I think these have produced a lot of interesting extra information on ionospheric current system, climatology of ionospheric currents at high latitudes. And I think these are fascinating. It's not something that I'm an expert in, but I think that there's a lot of advance being made there. And the interplay between Swarm mission, which is in low Earth orbit with very high accuracy magnetometers, and for example, things like Iridium Ampere mission, where we have many more magnetometers, 70 satellites, but with lower accuracy, lower resolution. There's some very nice interplay going on in the space physics mapping climatology of current systems. Yeah.
Thank you. Okay, Patrick has another question. Could local turbulent flow of magma leads to undipole behavior of magnetic field? Okay,
so I think the answer is yes, but let me qualify the question a little bit. So by magma, normally magma means hot silicate rock, like we have coming up at the mid-Atlantic ridge. This is normally like mantle or crust. remember it's the liquid iron in the core that is the crucial thing for the magnetic field. So I'm not sure if magma normally has a specific chemical composition. So it's really the iron in the core. And yeah, so as Patrick says, it's turbulent. And if you had some eddy, some local eddy in some turbulent vortex, then for sure this will produce a local current. That means a local source of magnetic field, and that is very different to this global dipole. That is the kind of first order picture of the Earth's magnetic field. So for sure, it's the localized structure of the current systems. And by current systems, I mean of the motions of the liquid metal that is producing this non-dipole behavior. So I would agree with his sentiment there.
Yeah, thank you. Okay, last question. Okay, and again, little different field. Let me read it. How strong is the radiation that you mentioned in the South Atlantic anomaly? How is it relevant? Okay. Has it some relevant impact on ground technology or aviation or human health?
Yeah, so it's mostly, this is mostly an issue for at satellite altitude, in low Earth orbit. So not at ground level, okay? Yes. So because you have the atmosphere in between, which is of course the very high energy charged particles will go right through. But the reason for this enhancement in the South Atlantic region, yeah, this is mostly an issue at low Earth orbit.
Yes.
So I would say it has perhaps, I think it's still under study, but it certainly has an impact on technology in low Earth orbit. You have to design your satellites to take the radiation dose that you expect in the South Atlantic anomaly. And for that, you need to have some guess about how it's going to evolve over the lifetime of your satellite mission. So, and also if you get some very large event in the sun, for example, then of course this is where you will feel more effects in the South Atlantic anomaly region. But I think there's no strong evidence with the current Earth's magnetic field that there are strong impacts on the ground. So I think this is more a question for satellites, maybe the International Space Station. Yes. And of course, with more and more low Earth orbit satellites, it is a relevant concern. There are cases of satellites having problems in the South Atlantic anomaly, especially if the electronics are not carefully designed to be handling upsets. So I think this is a question the engineers have to design the hardware to handle that.
There are models which this guy could use. I don't know. I will recommend SPENVIS. There are models of the trapped particles in magnetosphere. You could look at SPENVIS, for example. So thank you very much for all the answered questions, for the interesting topic, and I could again wish you just be very, very long active mission, and I will even say as Voyager for really decades. So thank you very much again.
Thank you, Pavel, and thanks for the invitation and for the good questions from everyone. Thank you.
Prichodili na tieto webináre